somewhere along the equator, in the middle of the widest ocean on the planet. A string of buoys floats quietly on the surface of the water. Each one is anchored to the seafloor by a long cable. Each one carries instruments that measure the temperature of the water at different depths. And each one sends its readings up to a satellite passing overhead, day after day, without pause. Most of the time, almost nobody outside a small community of ocean and climate scientists pays much attention to what these buoys are reporting. The numbers drift up a little, drift down a little, and the ocean goes on being the ocean then, every few years. Something in that steady stream of numbers changes, and a very old, very large, very slow-moving story begins to unfold again across the Pacific. That is roughly where this one begins. In the spring of 2026, buoys spread along the equator from the islands of Indonesia to the coastline of Ecuador started reporting a warming trend in a particular stretch of the Central Pacific, one that only months earlier had not been expected to arrive so quickly or so strongly. Underneath the surface, something large and slow was already sliding east, a body of unusually warm water, sitting roughly 150 meters down, stretching for thousands of kilometers along the equator, moving at the unhurried pace of what oceanographers call an equatorial Kelvin wavenon. Of this would mean very much on its own. Ocean temperatures wobble constantly, and warm patches come and go without consequence. What makes this particular kind of warming worth sitting with is that it belongs to a pattern that has shaped weather across nearly the entire planet. Again and again, for as long as people have kept careful records, and very likely for a long time before that. The pattern has a name that sounds almost gentle for something with this much reach. It is called El Niño, to understand what is stirring in the Pacific right now. It helps to slow down first and start somewhere calmer, with what the ocean and the sky above it are doing in an ordinary year. When nothing unusual is happening at all. Picture the Pacific stretched out along the equator, from the coast of South America in the east to the islands of Indonesia and northern Australia in the west. Most of the time, a steady wind blows across the surface of this stretch of ocean, moving from east to west, from Peru and Ecuador toward the western Pacific. These are the trade winds, and on any given day they are not especially dramatic. They are simply persistent. They blow gently but continuously, hour after hour. For months and years at a stretch, a wind blowing steadily over water for long enough will eventually move that water. Not far and not fast, but far enough and consistently enough to matter. And this is exactly what the trade winds do to the surface layer of the Pacific. They drag the warmest water westward and pile it up against the islands of the western Pacific, so that over time the sea surface in the far western Pacific sits measurably higher than the sea surface off the coast of South America, by something in the neighborhood of half a meter. It is a small tilt spread across an enormous distance. But it is a real one, and it is held in place day after day. By the wind, water pushed away from one place has to be replaced from somewhere else, and along the coast of Peru and Ecuador, that replacement rises from below. As surface water is dragged westward, cold water from deep in the ocean wells up to take its place. A process oceanographers simply call upwelling. This upwelling is not a minor detail. It is what keeps the eastern Pacific measurably cooler than the western Pacific, by something like 8 degrees Celsius, and it is also what makes the waters off Peru so productive. The cold water rising from below carries nutrients that have settled out of the sunlit layer over long stretches of time, and those nutrients feed the plankton, which feed the anchovies. which in turn feed the seabirds and support one of the largest fishing economies on Earth underneath this whole arrangement, at a depth that shifts depending on where you are in the basin, sits an invisible boundary called the thermocline. Above it, sunlight has warmed the water into a buoyant surface layer. Below it, the water is cold, dense, and largely undisturbed by whatever the atmosphere happens to be doing on a given day. The thermocline is not a hard wall so much as a zone where temperature drops off quickly with depth, and it behaves, physically, the way any boundary between two fluids of different density behaves. It resists mixing, and it can carry its own slow waves along its surface, much the way the ocean's actual surface carries the waves we can see because the trade winds have piled warm water into the western Pacific. The thermocline there sits deep, often more than 150 meters down, buried beneath a thick cushion of warm water. In the east, where cold water is being pulled up from below, the thermocline sits far closer to the surface, sometimes within 50 meters of it. The whole basin, ocean and thermocline together, is tilted, and it is held in that tilted shape by the very same wind that piles surface water to the west. The atmosphere above this tilted ocean settles into a matching, cooperating pattern of its own. Warm water in the western Pacific evaporates readily, feeding towering columns of moist air that rise, cool, and release their moisture as some of the heaviest rainfall found anywhere on the planet, concentrated over Indonesia and the seas around it. Having released its moisture, that air, now high in the atmosphere, drifts back eastward before sinking over the far cooler waters of the eastern Pacific, where the air is drier and rain is much less frequent. Once it sinks, it flows westward again along the surface as the trade winds themselves, closing the loop. Ocean and atmosphere moving together in a single connected circuit. Meteorologists call this loop the Walker circulation, and it is one of the more important, if less famous, engines of the planet's weather, quietly organizing rainfall and dry seasons across a wide swath of the globe, year after year, largely unnoticed by anyone who does not study it for a living. This entire arrangement, the tilted ocean, the deep thermocline in the west, and the shallow one in the east, the rising air over Indonesia and the sinking air over the eastern Pacific, is what an ordinary year in the tropical Pacific looks like. It is not perfectly static. It wobbles a little from season to season, but broadly it is stable, and broadly it is self-sustaining, holding its shape for years at a stretch, the way a spinning top holds its shape as long as nothing knocks it off balance. El Niño begins when something does knock it off balance. Specifically, it begins when the trade winds weaken. Nobody fully understands why the trade winds weaken when they do. This is one of the genuinely open questions sitting at the heart of El Niño research, and different scientists point to different possible triggers. A chance burst of westerly wind over the far western Pacific, an internal wobble in the coupled ocean-atmosphere system, or some combination of influences that current models still struggle to identify with confidence ahead of time. What happens next, though, once the winds do weaken, is much better understood, and it is worth walking through slowly once the trade winds relax. Even slightly, the tilted ocean is no longer being held in its usual shape. The warm water piled up in the west begins sliding back east, not as a wave crashing onto a shore, but as a slow, deep pulse of warmth traveling along the thermocline, taking weeks to cross the Pacific basin. This is the downwelling Kelvin wave, the same kind of wave that, in the spring of 2026, instruments detected moving east beneath the surface of the Pacific. As it travels, it pushes the thermocline down ahead of it, deepening the warm surface layer wherever it passes by, the time this pulse of warmth reaches the coast of South America. It has done something with consequences reaching far beyond the ocean itself. It pushes the thermocline down along a coastline that depends on a shallow thermocline for its cold, nutrient-rich upwelling. With the thermocline pushed deeper, upwelling can no longer reach cold water, and the water rising to the surface off Peru and Ecuador arrives warmer than it should. The Eastern Pacific, ordinarily the cool side of the basin, begins to warm. This warming does not stay isolated for long. It changes the temperature contrast that the whole system depends on. And when that contrast changes, the winds respond. And when the winds respond, the ocean responds again in turn. That back and forth, ocean and atmosphere leaning on each other, each one amplifying whatever the other just did, is the true engine of El Niño. And it deserves to be taken slowly, one step at a time. Before going any further, picture the two sides of the Pacific as opposite ends of a very long seesaw, one connected not by a rigid beam but by wind and water temperature. Under ordinary conditions, the Eastern Pacific is cool and the Western Pacific is warm, and that contrast is precisely what keeps the trade winds blowing. Warm air rises over the west, cool air sinks over the east. And the pressure difference between the two drives wind from east to west along the surface, which is the very same wind that keeps the ocean tilted and the contrast in place. Ocean and atmosphere are holding each other up. Now suppose the Eastern Pacific warms, even slightly, the way it does once a downwelling Kelvin wave arrives off South America. The contrast between the cool east and the warm west shrinks. With less contrast, there is less pressure difference to drive the trade winds, so the winds weaken further. With weaker winds, even less warm water gets pushed westward, so even more warm water stays in the east, or is drawn further east by whatever surge is already underway. The east warms a little more. The winds weaken a little more. The east warms again. This loop, each step feeding the next, is called the Bjerknes feedback. And it is the single most important mechanism in the entire story of El Niño. It is what allows a small, almost unremarkable weakening in the trade winds to grow over a period of months into a full reversal of the Pacific's normal temperature pattern. Scientists who study complex systems recognize this shape immediately. It is a positive feedback loop, meaning a loop where each cycle reinforces the last rather than cancelling it out. Embedded inside a system where two different parts, ocean and atmosphere, are constantly responding to each other. What makes the Bjerknes feedback unusual, compared to most examples of runaway feedback loops in nature, is its timescale. It plays out over months, across a basin the size of the Pacific, rather than over the fractions of a second typical of feedback loops in, say, electronics or acoustics. It is a slow-motion amplifier, but it is still an amplifier, and once it engages, it has a genuine tendency to run away with itself. For a while, none of this would work the way it does anywhere else on the planet's surface. The reason the tropical Pacific can sustain waves like the Kelvin wave, waves that travel thousands of kilometers along the equator without spreading out or losing their shape, comes down to a subtle piece of physics involving the Earth's rotation. Away from the equator, the rotation of the Earth causes moving air or water to curve, an effect called the Coriolis effect, which is strongest toward the poles and which weakens steadily as you approach the equator, vanishing to zero exactly on it. This creates something close to a channel, a region straddling the equator where the usual rotational effects that curve and disperse motion elsewhere on the planet are largely absent. Oceanographers and atmospheric scientists call this the equatorial waveguide, and it behaves a little like a canal that keeps a boat moving in a straight line. Except here it is keeping a pulse of warm water or a pattern of rainfall, moving cleanly along the equator instead of spreading out and dissipating the way disturbances typically do at higher latitudes. Kelvin waves are one of the two main kinds of disturbance that travel through this equatorial channel, and they only move in one direction, eastward, hugging the equator, carrying warm water and a deepened thermocline ahead of them at a steady pace of roughly 2 to 3 meters per second, which is fast by oceanic standards, even though it still takes such a wave several weeks to cross the full width of the Pacific. The other main kind of disturbance is the Rossby wave, and Rossby waves are, in almost every way, the mirror image of Kelvin waves. They travel only westward, they move roughly a third as fast, and rather than deepening the ones relevant to ending an El Niño event tend to lift it back up. This matters because nothing in the physical world runs away forever, and El Niño is no exception. Even as the Bjerknes feedback is amplifying the initial disturbance in the east, the same weakening of the trade winds that triggers a Kelvin wave heading east also triggers Rossby waves heading west, back toward Indonesia and the far western Pacific. These westward moving waves are, at first, a quieter part of the story. They take much longer to matter, 6 months to a year or more to cross the basin. But once they reach the western boundary of the Pacific, they reflect the way a wave in a bathtub reflects off the far wall, and they come back east as a different kind of signal, one that lifts the thermocline rather than deepening it. When this reflected signal finally arrives in the eastern Pacific, it lifts the thermocline back toward the surface. Cold water can reach the surface again through upwelling, and the temperature contrast between east and west begins to rebuild. Once the contrast rebuilds, the trade winds have a reason to strengthen again. And once they strengthen, the whole system tips back the other way. This interplay, a fast eastward signal that builds the event and a slow westward signal that eventually undoes it, is sometimes called the delayed oscillator mechanism, an idea formalized mathematically in 1988 by the atmospheric scientists Paul Schopf and Max Suarez. Their work helped explain something that had puzzled researchers for a long time, not just why El Niño happens, but why it eventually, reliably, ends, and why the whole cycle tends to repeat itself every few years rather than settling into either extreme permanently. Sometimes the system does not simply return to its ordinary, neutral state. It overshoots in the opposite direction, and the trade winds end up stronger than usual. Upwelling in the east becomes more vigorous than usual, and the eastern Pacific grows unusually cool rather than merely returning to normal. When this happens, the event has tipped into what is called La Niña, the cooler counterpart to El Niño, and its own set of consequences ripple outward across the planet in a pattern that is, in many places, close to the opposite of what El Niño produces. La Niña deserves its own unhurried explanation, and it will get one. But for now, it is enough to know that the Pacific does not simply sit in one state. It swings, gently and irregularly, between a warm phase, a cool phase, and long stretches of something closer to neutral. And the whole three-part cycle, warm, cool, and in between, is what scientists refer to collectively by a broader term, the El Niño Southern Oscillation, usually shortened to ENSO. El Niño is only one phase of a larger, ongoing conversation between the Pacific Ocean and the atmosphere above it. a conversation that has been running for as long as there has been an ocean and an atmosphere to have it, and one that people only began to understand in any real scientific sense within the last century and a half. That understanding did not arrive all at once, and it did not arrive from a single place. It came together slowly, from fishermen who noticed something bothering their catch, from a mathematician sent halfway around the world to solve an entirely different problem, and from a scientist who happened to have access to instruments nobody before him had ever had. It is a story worth telling in full, because it says almost as much about how science actually progresses as it does about the ocean itself. The earliest people to notice El Niño were not scientists at all. They were fishermen working the coast of Peru and Ecuador in the late 1800s. And what they noticed was not a number on a chart, but a disruption to their livelihood. Every so often, roughly every few years, the cold current that normally ran along their coast would weaken or stop altogether, replaced by a slab of unusually warm water. When that happened, the anchovies that the entire local economy depended on would vanish from their usual grounds. The seabirds that fed on those anchovies would struggle and sometimes starve in large numbers, and the fishing catch would collapse. Sometimes for months at a stretch, the warm water tended to show up around Christmas, which is how it got its name. Fishermen called it El Niño, a reference to the Christ child, a name that carries a strange gentleness for something that could devastate a season's income. For a long time, the phenomenon stayed a local story, known and dreaded along a particular stretch of coastline, but unknown to the wider world. The first attempt to describe it in scientific terms came in 1892, when a Peruvian sea captain named Camilo Carrillo presented an account of the warm current to the Lima Geographical Society. To Carrillo and his contemporaries, this was an interesting local oceanographic curiosity, worth documenting and worth understanding on its own terms, but nothing more than that. Nobody at the time, including Carrillo himself, suspected that the same patch of warm water off South America might have anything to do with weather patterns unfolding on the far side of the planet half a world away, and without any awareness of the Peruvian fishermen or their warm current. A British mathematician named Gilbert Walker was working on an entirely different problem, one with much higher stakes attached to it. In the early 1900s, Walker had been sent to India to help solve the recurring puzzle of the monsoon. When the seasonal rains that much of South Asia depended on for agriculture failed to arrive on schedule, the result was famine, and the British colonial administration, having been caught off guard by several catastrophic failures already, wanted a way to predict when the monsoon might fail again. Walker had no working theory to build from, so he did what a mathematician with a large amount of data and no theory tends to do. He collected records, enormous quantities of them, from weather stations scattered across the globe, and he searched for patterns. What he eventually found, buried in decades of pressure readings, was a strange and consistent relationship. When air pressure at the surface was high over the eastern Pacific, it tended to be low over Indonesia and the eastern Indian Ocean, and when it was low over the eastern Pacific, it tended to be high over Indonesia. The two regions behaved like opposite ends of a seesaw, one going up as the other went down, and the swings between them tracked closely with weather a given years. Indian monsoon turned out strong or weak by the 1920s. Walker had a name for this seesaw pattern. He called it the Southern Oscillation. What he did not have, and what he would never have during his own lifetime, was any idea of what was actually causing it. He had found a genuine, statistically robust pattern using exactly the right kind of data and exactly the right mathematical tools for the job. But the physical mechanism behind the pattern was hidden from him, because it lay in a place he had no way of observing directly. Beneath the surface of an ocean thousands of kilometers from where he was working. Walker died in 1958, still without an answer. It is worth pausing on that for a moment, because it captures something that happens more than once in the history of science. A pattern can be entirely real, entirely visible in the data, and still remain unexplained for decades, simply because the tools needed to see its actual cause do not yet exist. Those tools finally arrived in the 1960s, in the hands of a Norwegian meteorologist named Jacob Bjerknes, who was by then working at the University of California. Bjerknes had access to something neither Walker nor Carrillo's generation had ever had: early satellite observations of the tropical Pacific, combined with a growing network of ocean buoys capable of measuring sea surface temperature in some form of real time. When Bjerknes laid this ocean temperature data alongside Walker's decades-old pressure records, the connection between the two was, in his own later description, almost embarrassingly obvious once seen. The warm water off the coast of South America that Peruvian fishermen had been naming and dreading for generations was the very same phenomenon as the atmospheric seesaw that Gilbert Walker had spent his career chasing without ever identifying its source. They were not two separate curiosities. They were one coupled system, ocean and atmosphere locked together, each one driving the other and each one being driven by the other. In turn, Bjerknes published the paper that tied these threads together in 1960, and in doing so, effectively founded the modern scientific study of El Niño within the span of a single article. He gave the atmospheric half of the loop its name too, calling it the Walker circulation, in a deliberate tribute to the mathematician who had spent decades studying its effects, without ever seeing the ocean mechanism underneath it. It was, in a sense, a quiet act of scientific generosity, naming a discovery after someone who had contributed a crucial piece of it, but had died a decade earlier without knowing how close he had come to the full picture. What Bjerknes offered the field went beyond simply connecting to known phenomena. He introduced a genuinely new way of thinking about feedback within the climate system. The idea that a small nudge in one part of a coupled system, ocean or atmosphere, could amplify itself through the response of the other part, growing into something far larger than the initial nudge alone could explain. That single insight, the same feedback loop described a little earlier in this telling, is what makes El Niño possible at all, and it is also what explains why some years produce only a mild, forgettable warming while others grow into events that reshape weather patterns across entire continents. The difference between an unremarkable El Niño and a historically significant one comes down to how far, and for how long, that feedback loop is allowed to run before something interrupts it. This raises a natural question, one that sits in front of every forecaster currently watching the Pacific. What exactly separates an ordinary El Niño from the kind that ends up in history books? And how do scientists actually decide? In formal terms, where that line falls, there is, as it turns out, no such thing as a super El Niño, at least not in any official sense. The phrase does not appear in any classification system used by the scientists who actually study these events. It is a term that grew out of headline writing, a convenient way to describe the events that broke past whatever measuring stick had been used before them. The scientists themselves rely on quieter, less dramatic language, and that quieter language turns out to matter quite a bit. What forecasters actually track is something called the Oceanic Niño Index, which is a 3-month rolling average of how far the sea, Surface temperature in a specific patch of the Central Pacific departs from its long-term average. That patch is called the Niño 3.4 region, and it sits directly on the equator, centered roughly on the longitude of the Galapagos Islands, stretching westward across several thousand kilometers of open ocean, bounded by 5 degrees north and 5 degrees south latitude, and by 120 degrees west and 170 degrees west longitude. These particular boundaries were not chosen arbitrarily. Decades of research showed that sea surface temperature variability within this specific box correlates more reliably with weather changes far beyond the tropics than variability measured anywhere else in the Pacific. It functions almost like a narrow channel through which the entire El Niño signal reliably passes, making it, in practical terms, the single most useful patch of ocean on the planet to monitor if the goal is understanding what the rest of the climate system is about to do. Sea surface temperatures across that region are tracked continuously, using a combination of moored ocean buoys and satellite-based infrared measurements. And when the 3-month average temperature in the Niño 3.4 region climbs to half a degree Celsius above the long-term average and stays there for 5 overlapping seasons in a row, an El Niño event is formally declared. If the temperature instead falls half a degree below average and holds there, the event is classified as La Niña. From that starting point, the categories used to describe intensity are fairly simple. An index reading between half a degree and just under 1 degree above average is called a weak event. Between 1 degree and just under 1.5 degrees is moderate. Between 1.5 and just under 2 degrees is strong. And anything at 2 degrees or higher is classified as very strong, which is the formal category that headlines translate loosely into super very strong events. By this definition, are genuinely rare. Across the entire instrumental record, which extends back to 1950, only 3 of them have occurred. The first arrived in 1982 and 1983, catching the world's forecasters almost entirely by surprise, since the observing network at the time was thin enough that nobody recognized what was building until it had already arrived. The second arrived in 1997 and 1998, peaking at an index of roughly 2.4, and for a long stretch afterward stood as the most intense El Niño ever measured by modern instruments. The third arrived in 2015 and 2016, edging just past the 1997 event with a peak around 2.6, narrowly taking the record for itself. Numbers on a chart, though, tend to flatten out what actually happened underneath them. A line that rises to 2.4 and falls back to neutral over the course of a year looks, on paper, like a temporary blip. What that line does not show is what unfolded on the ground while the warm water sat where it should not have been. The 1982 to 1983 event, arriving as it did with almost no warning, caused what one assessment later described as the largest synchronized crop failure the modern world had experienced up to that point. A study published in Nature Climate Change in early 2026 went back and attempted to quantify its long-term human cost using methods that had not been available to earlier researchers. The study found that average life expectancy across countries bordering the Pacific fell by roughly half a year in the aftermath of that event and stayed measurably depressed for years afterward. A loss the researchers translated into a monetary equivalent of somewhere around 2.6 trillion United States dollars. The 1997 to 1998 event, the one many people alive today still remember directly, brought flooding to Peru. drove peatland fires across Indonesia and Borneo that blanketed 6 countries in smoke for months, and produced storms in California severe enough to wash out highways and trigger mudslides through entire neighborhoods. The global death toll officially attributed to weather events connected to that El Niño came to roughly 23,000 people. The same kind of long-term economic analysis applied to the 1982 event found that the 1997 event reduced life expectancy across the Pacific Rim by close to 4/10 of a year, translating to a monetary equivalent loss of around 4.7 trillion United States dollars, while a separate analysis published in the journal Science estimated total global income losses from that same event at closer to $5.7 trillion, with most of that burden falling on tropical countries least able to absorb it, the most recent of the three. The 2015 to 2016 event did something the earlier two had only hinted at. It killed coral on a scale nobody had documented before, the marine heat wave that arrived alongside that. El Niño produced the worst coral bleaching event ever recorded on the Great Barrier Reef, with surveys afterward finding that roughly a third of the reef's northern and central sections had suffered significant coral mortality. Bleaching of comparable severity struck reefs across the Indian Ocean, the Caribbean, and the Central Pacific in the very same window of time. The same event pushed Peru's Oncaveta fishery, the largest single-species fishery on the planet, close enough to collapse that the government cancelled the year's second fishing season outright. And in the atmosphere above all of this, the heat that the event pumped out of the Pacific helped make 2016 the hottest year ever recorded up to that point, breaking a record that had only been set the year before. What stands out, looking at these three events side by side, is how little the warm water itself actually traveled. In every case, it stayed within the tropical Pacific, never wandering more than a few thousand kilometers along the equator, and yet the consequences reached India, Indonesia, Zimbabwe, California, and the reefs of the Great Barrier, thousands upon thousands of kilometers from where the warming actually occurred. Understanding how a patch of warm water in the middle of one ocean manages to reach that far is its own piece of the story, and it deserves its own unhurried attention a little further along before that. Though there is a complication worth sitting with, because it explains something genuinely strange happening to the numbers used to measure El Niño today. 0.5 degrees Celsius above average meant something very specific in 1982, when the average itself reflected a cooler planet. It means something subtly different now, because the entire tropical Pacific, along with the tropical Atlantic and the tropical Indian Ocean, has warmed measurably over the intervening decades. This is not simply a matter of recalibrating a number. It is closer to a conceptual problem, the oceanic equivalent of measuring someone's height against a yardstick that has itself been quietly stretching. If the standard used for comparison is drifting in the same direction as the thing being measured, the comparison starts to lose some of its meaning. Climate scientists have not ignored this problem. In response, a newer measure has come into use, called the Relative Oceanic Niño Index, which compares the temperature of the Niño 3.4 region not against a fixed historical baseline from decades past, but against the temperature of the rest of the tropical oceans as they stand right now. The thinking behind the change is fairly intuitive, once stated plainly. If an entire body of water is warming everywhere at once, then measuring one small patch of it against a 30-year-old baseline mostly tells you about the warming of the whole ocean, not about whether that particular patch is doing anything unusual. Comparing it instead to its neighbors, measured at the same moment, isolates the genuine signal from the rising tide underneath it. The category names and the numerical thresholds used to define weak, moderate, strong, and very strong events have not changed. What has changed is the reference point those categories are measured against. A shift closer in spirit to physics, moving from an absolute frame of reference to a relative one than to any simple correction of an old mistake. None of this measuring would be possible without an enormous, patient infrastructure of instruments scattered across the Pacific. And that infrastructure itself has an origin story worth telling, because it grew directly out of the failure to see the 1982 event coming before 1982. The tropical Pacific was sparsely instrumented. Ships passing through occasionally logged surface temperature readings, and a handful of scattered stations recorded what they could. But there was nothing resembling a continuous, basin-wide picture of what the ocean was doing beneath the surface. When the 1982 to 1983 event arrived, it did so almost invisibly, and by the time its effects were unmistakable on the ground, the ocean had already fully tipped into one of the most intense events of the century. The scientific community's response to that blind spot was to build something that had never existed before: a permanent, basin-scale ocean observing system, purpose-built to watch for the next one. Arriving an oceanographer named Klaus Wertke had, some years earlier, proposed a theoretical framework suggesting that El Niño events were preceded by a gradual build-up of warm water in the western Pacific, driven by sustained trade winds, which then discharged eastward once the winds relaxed. Testing that idea properly required exactly the kind of continuous, real-time measurement that did not yet exist, and Wertke's proposal became one of the intellectual foundations for the observing system that followed. Between 1985 and 1994, an international research effort called the Tropical Ocean Global Atmosphere Program, generally known by its acronym TOGA, coordinated the deployment of a network of moored buoys stretched across the equatorial Pacific, each one anchored to the seafloor and instrumented to measure temperature at multiple depths, along with wind speed, humidity, and other surface conditions, transmitting its readings by satellite in something close to real time. This became known as the Tropical Atmosphere Ocean Array, later expanded and upgraded under the name Dow/Triton, with the American oceanographer Michael McFadden playing a central role in its design and long-term operation through NOAA's Pacific Marine Environmental Laboratory. It is this same array of buoys, still operating today, decades after its first components were dropped into the water, that detected the warming described at the very start of this account. The buoy array was never meant to work alone. Over the following decades, it was joined by two other major observing systems, each filling in a different piece of the picture. The first is a global fleet of autonomous instruments called Argo floats, several thousand of them drifting freely throughout the world's oceans, each one periodically sinking to a depth of about 2,000 meters, drifting for roughly 10 days, then rising back to the surface while recording temperature and salinity throughout the water column, before transmitting its data by satellite and sinking again to repeat the cycle. Argo floats extend the picture the moored buoys provide, offering a broader, if less continuous, view of ocean heat content across the entire globe. Not just the tropical Pacific, the second edition came from space. Beginning in 1992, a satellite mission called Topex/Poseidon, a joint effort between the American and French space agencies, began measuring the height of the ocean's surface from orbit with remarkable precision, down to a matter of centimeters. Sea surface height turns out to be an unusually good proxy for the depth of the thermocline and the amount of heat stored in the upper ocean. Since warmer water expands and quite literally sits higher than cooler water of the same mass. That satellite mission was followed by a succession of others carrying the name Jason, extending an unbroken record of global sea surface height that now spans more than 3 decades, and giving scientists a way to watch the tilt of the Pacific and the progress of Kelvin waves moving across it. From orbit taken together, the moored buoys, the profiling floats, and the satellite altimeters form a layered observing system, unlike anything that existed before the 1982 surprise. And it is precisely this system that allowed scientists, in the spring of 2026, to identify a Kelvin wave forming and moving east months before its effects would be felt on any coastline. Detecting a Kelvin wave is one thing. Turning that detection into a usable forecast of what the atmosphere will do in response is a separate and considerably harder problem, and it too has its own history. The first real breakthrough came in the mid-1980s, when 2 researchers at Columbia University's Lamont Doherty Earth Observatory, Mark Kane and Stephen Zebiak, built a coupled model, one that simulated the ocean and atmosphere together rather than treating them separately, capable of simulating the physics of the Bjerknes feedback loop described earlier in this account. In 1986, their model produced something no one had achieved before, a real-time forecast of an approaching El Niño event, issued months in advance and subsequently borne out as the event unfolded. It was, by most accounts, the first successful dynamical prediction of an El Niño, and it opened the door to the modern era of seasonal climate forecasting. Forecasting forecasting has grown considerably more sophisticated since then. Modern outlooks typically combine 2 broad approaches: statistical models, which look for patterns in historical data resembling current conditions, and dynamical models, descendants of the Kane-Zebiak approach, which simulate the physical equations governing ocean and atmosphere directly, run forward in time on some of the most powerful computers available to climate science. Forecasters rarely trust any single model in isolation. Instead, they run ensembles, sometimes dozens of simulations from multiple independent modeling centers around the world. Each started from slightly different initial conditions, and look at how much those simulations agree or disagree with one another as a rough measure of confidence. Even with all of this infrastructure, El Niño forecasting carries a well-known limitation that researchers have studied for decades, generally referred to as the spring predictability barrier. Forecasts of ENSO conditions initialized during the Northern Hemisphere spring consistently show less skill than forecasts made at other points in the year. And while the exact reasons remain a subject of ongoing research, the leading explanations point to the fact that the ocean-atmosphere system tends to be making its transition between states at exactly that time of year, when the signal is weakest relative to its natural noise, and small errors in the starting conditions of a model have the most room to grow before the following winter. This is part of why the initial warnings about the current event, first raised by forecasters in March, carried genuine uncertainty even as the underlying ocean signal continued to strengthen through the following months. The ocean tends to reveal its true intentions more clearly by late summer, once the spring barrier has passed, which is precisely the point in the calendar this particular event is now approaching. These forecasts, once produced, rarely stay confined to research papers and weather agency bulletins. National governments and industries across the Pacific Rim and well beyond it have over the past few decades built ENSO outlooks directly into their planning calendars. Agricultural ministries in Australia and Peru use seasonal forecasts to advise farmers on planting schedules months before a growing season begins. Since knowing in advance whether the coming season is likely to run unusually dry or unusually wet can meaningfully change which crops make sense to plant and how much irrigation to plan for. Water utilities across the southwestern United States factor ENSO outlooks into reservoir management. Since a La Niña winter carries a meaningfully higher chance of drought than an El Niño winter does in that region, international aid organizations have, in a number of documented cases, used early El Niño forecasts to pre-position food and medical supplies in regions of eastern and southern Africa with a well-established history of ENSO-driven flooding or drought, shaving weeks or months off emergency response times, compared with waiting for a crisis to become visible on the ground before mobilizing. None of this makes the underlying forecasts perfect, and every agency using them builds in some allowance for the real uncertainty described throughout this account. But it does mean that the decades of investment in buoys, floats, satellites, and coupled ocean atmosphere models has translated into something more than academic understanding. It has become a working part of how a meaningful share of the planet prepares for a recurring disruption that, unlike most natural disasters, arrives with months of genuine advance warnings. The three very strong events of the instrumental era are not, however, the largest El Niño disruptions known to history. They are simply the largest ones caught by modern thermometers and buoys. An earlier event, less precisely measured but extensively documented through written records at the time, arrived in the mid-1870s and stands, by some assessments, as the deadliest climate-related disaster of the modern era between 1876 and 1878. The monsoon failed across India for 2 consecutive years. At almost the same time, rains collapsed across northern China, and crops failed across the northeast of Brazil. 3 widely separated regions experiencing agricultural catastrophe within the same narrow window of time. A pattern that only makes sense once you understand how a single ocean disturbance in the Pacific can reach so many distant places at once. A mechanism this account will return to shortly. The historian Mike Davis, who researched this period in detail for his book Late Victorian Holocausts, documented how famine spread across 3 continents in close succession, how cholera and malaria moved through populations already weakened by hunger, and how colonial administrative failures compounded a natural disaster into something far worse than the weather alone would have produced. Estimates of the total death toll vary considerably depending on the historian and the methodology used, but figures cited by sources including NASA's Earth Observatory place the range somewhere between 30 and 60 million people. For comparison, historians generally estimate total deaths from the First World War, military and civilian combined, at around 20 million. The El Niño of the 1870s, by the more conservative end of that range alone, killed more people than that global war would decades later. And the overwhelming majority of those who died almost certainly never connected their suffering to a patch of warm water sitting in the middle of the Pacific Ocean events. Like this raise an obvious question. How far back does this pattern actually go? And how would anyone know, given that reliable instruments only extend back to the middle of the 20th century? The answer comes from a branch of science called paleoclimate, which reconstructs past climate conditions from natural materials that record their environment as they form. The same general principle behind reading tree rings to determine a tree's age extended to far more exotic archives, One of the most productive of these archives turns out to be coral. Corals build their skeletons in the ocean, layer by layer, incorporating oxygen atoms from the surrounding seawater as they grow. And the ratio between different forms of oxygen, differing slightly in atomic weight, shifts in a measurable way depending on the temperature and composition of the water the coral was growing in at the time. By drilling into old coral formations, some living and some long dead but preserved on the sea floor, and analyzing thin slices along their growth bands the way a geologist might read rock strata, researchers have been able to reconstruct sea surface temperature and rainfall patterns stretching back thousands of years. Coral records recovered from Central Pacific including work led by the geochemist Kim Cobb and colleagues examining formations near Kiritimati and Palmyra Island, have extended the record of El Niño activity across multiple past centuries and, using older and more fragmentary fossil specimens, deep into the more distant past. A second major archive comes not from the ocean but from a lake, Lake Palcacoca in the Andes of southern Ecuador, sits in a location where unusually heavy rainfall, of the kind El Niño tends to bring to that part of South America, produces a distinctive flood layer of sediment on the lake bottom. Layer upon layer, year upon year, these flood deposits build up on top of one another, each one a rough record of whether a given year brought El Niño-style flooding or not. In a study published in the journal Science in 1999, the geologist Donald Rodbell and his colleagues extracted a sediment core from the lake and used these flood layers to reconstruct a record of El Niño activity stretching back roughly 15,000 years. One of the longest continuous records of its kind ever assembled, taken together. These proxy records, corals, lake sediments, and to a lesser extent tree rings from regions sensitive to El Niño-driven rainfall, tell a consistent story. El Niño is not a modern phenomenon, and it is not a symptom of anything unique to the current climate. It has been a recurring feature of the Pacific for many thousands of years, with its frequency and intensity shifting gradually over long stretches of time, apparently growing quieter during some multi-thousand-year windows and more active during others, likely tied to slow changes in the Earth's orbit and the resulting distribution of sunlight across the seasons. What these proxy records cannot do, however, is tell us what happens when an El Niño of historic intensity arrives inside a climate system that is, on average, already unusually warm from causes entirely separate from the Pacific itself. That specific combination, a very strong El Niño layered on top of a planet already carrying substantial background warming, simply does not appear anywhere within the multi-thousand-year window that corals and lake sediments can see, in the most literal sense available to science. This is uncharted territory, not because El Niño itself is new, but because the ocean it would be occurring within is not the ocean any of its historical predecessors ever occurred within. This is a good point to return to a question raised earlier and set aside. How does a patch of warm water sitting on the equator in the middle of the Pacific manage to cause drought in southern Africa, weaken the Indian monsoon, and quiet down hurricane activity in the Atlantic, all at roughly the same time? The answer involves a concept climate scientists call teleconnections, a fairly clinical-sounding word for something that behaves, physically, much more like ripples spreading outward from a stone dropped into still water. The mechanism begins with rainfall. Under ordinary conditions, as described earlier, towering thunderstorms cluster over the warm waters surrounding Indonesia, driven by the Walker circulation. During El Niño, as the warmest water shifts eastward with the developing Kelvin wave, those same thunderstorms shift with it, sometimes by thousands of kilometers. This sounds, on its face, like a fairly local change, a shift in where it happens to rain. But those thunderstorms are doing far more than producing local rainfall. They are the mechanism by which heat and moisture gathered from the ocean's surface get carried upward into the top of the troposphere, the layer of atmosphere where the jet streams live, and where much of the weather steering the rest of the planet actually takes shape. When the thunderstorms relocate, the injection of heat into the upper atmosphere relocates with them, and shifting where heat enters the upper atmosphere reliably shifts the path the jet streams take. The jet streams are fast-moving rivers of air that steer weather systems across entire continents, and moving them even slightly can send a storm track that would ordinarily cross one region drifting hundreds of kilometers toward another instead. These shifts propagate outward from the tropics as large-scale standing wave patterns in the atmosphere, locking certain regions into unusual conditions, wetter than normal or drier than normal, for months at a stretch. Southern Africa has, over the past century and a half, learned this lesson repeatedly. During a strong El Niño, the rains that would ordinarily fall across Zimbabwe, Botswana, Namibia, South Africa, and the southern half of Mozambique between December and February tend to fail. The El Niño of 1991 and 1992 produced what the region still remembers as its worst drought in a century, an event that researchers at the University of Arizona's Water Resources Center have estimated affected somewhere around 86 million people, close to 3/4 of the region's population at the time. More recently, the El Niño spanning 2023 and 2024 drove water levels at the Kariba Dam so low that hydroelectric generation for both Zambia and Zimbabwe effectively collapsed, leaving entire cities dependent on rolling blackouts for months. East Africa, only a relatively short distance north, tends to experience the opposite pattern, with rainfall increasing during El Niño years, sometimes to a degree that causes serious flooding, displacement, and crop damage in its own right. The longer shadow in this region, though, tends to arrive afterward in the form of disease. Researchers studying El Niño-sensitive parts of East Africa have found that cholera cases can triple during and after these events, as standing floodwater and damaged sanitation systems create exactly the conditions the bacteria responsible for cholera need in order to spread. The connection between El Niño and infectious disease reaches further than cholera alone. Studies drawing on multiple epidemiological datasets have identified clear ENSO-related signals in the incidence of malaria, dengue fever, Rift Valley fever, and hantavirus, all diseases whose transmission depends heavily on temperature and rainfall patterns that shape the habitat and breeding cycles of the mosquitoes, rodents, and other organisms that carry them. Seen this way, El Niño is not simply a climate event confined to the ocean and atmosphere. It is, in a very real sense, a force that reshapes disease risk across entire regions, unevenly distributed but reaching nearly every inhabited continent in some form. Indonesia and the wider Western Pacific experienced the reverse problem from East Africa, with the thunderstorms that would normally deliver monsoon rainfall pulled eastward. The region dries out, and dry rainforest tends to burn. The Indonesian peatland fires of 1997, which blanketed 6 countries in smoke for months, were not a freak accident of arson or carelessness. They were what happens when an unusually dry rainforest sits atop a deep layer of peat. And El Niño was the mechanism that dried that rainforest out in the first place. Northern Australia experiences a broadly similar pattern of drought and elevated fire risk, while the southern half of the country tends to respond in less predictable ways, depending on the particular character of a given El Niño. The Indian monsoon occupies a slightly more careful position in this story, because while the link to El Niño is real, it is not absolute. Strong El Niño events tend to weaken the summer monsoon that roughly 1 billion farmers across South Asia depend on for their livelihoods. But there are well-documented years in which a strong El Niño arrived and the monsoon nonetheless turned out close to normal. The relationship is statistical rather than mechanical, and other factors, particularly the state of a separate ocean pattern called the Indian Ocean Dipole, can either reinforce or partly cancel out the influence of a given El Niño on any particular year's rainfall. The Atlantic Ocean, meanwhile, tends to receive what is, for once, a genuinely favorable side effect. When the Central Pacific warms during a strong El Niño, it alters wind patterns high above the Atlantic basin in a way that increases what meteorologists call vertical wind shear, a change in wind speed and direction with increasing altitude. Tropical storms depend on a stable, largely undisturbed column of rising warm air to organize and intensify, and strong wind shear tears that column apart before it has a chance to strengthen into a hurricane. The practical result, most years, is fewer hurricanes, weaker hurricanes, and a quieter Atlantic season overall, though forecasters are always careful to note that a quieter season lowers the odds of a destructive storm without eliminating them. And even historically quiet Atlantic seasons have produced individual storms capable of serious damage. There is also a pattern connecting El Niño to winter weather across North America, one meteorologists refer to as the Pacific North American pattern. During a strong El Niño winter, the southern tier of the United States, from California across the Gulf Coast to Florida, tends to see wetter and stormier conditions than usual, while the Pacific Northwest and parts of the Ohio Valley tend to run milder and drier than usual. As with the Indian monsoon, this is a statistical tendency rather than a guarantee, and any individual winter can depart from the pattern considerably. Even the planet's carbon cycle carries a detectable ENSO signature. Strong El Niño years tend to coincide with faster than usual growth in atmospheric carbon dioxide concentrations, measured at monitoring stations such as the one atop Mauna Loa in Hawaii. Part of the reason involves the same droughts already described in Indonesia and the Amazon. Dry conditions reduce how much carbon growing vegetation can absorb from the atmosphere, while also increasing the risk of fires that release stored carbon back into it, temporarily weakening the land's ability to offset the carbon dioxide that human activity continues to add. And the disruption to fisheries reaches well beyond the oncoveta stocks off Peru already described. Warmer than usual waters during strong El Niño events have been linked to disrupted salmon runs along the Pacific coast of North America, shifts in the distribution of squid fisheries across the eastern Pacific, and altered migration patterns among numerous other commercially important species, each adjustment rippling outward into the economies and communities that depend on those fisheries for their livelihood. Of this has been describing one half of a two-part cycle, and it would be incomplete without giving proper attention to the other half. La Niña, the cooler counterpart to El Niño, tends to receive far less public attention, perhaps because its effects, while significant, rarely produce the same dramatic imagery as coral bleaching or Indonesian wildfires. But it is every bit as consequential a phase of the same underlying system, where El Niño begins with weakening trade winds, La Niña is associated with trade winds that strengthen beyond their usual intensity. Stronger winds pile even more warm water into the western Pacific than usual, deepen the thermocline there further, and drive more vigorous upwelling of cold water along the coast of South America, so that the eastern Pacific ends up measurably cooler than its already cool average state. In many respects, La Niña simply pushes the ordinary, neutral arrangement of the Pacific further in its usual direction. Rather than reversing it the way El Niño does, the regional consequences of La Niña tend to mirror those of El Niño in reverse, though not with perfect symmetry. Where El Niño tends to bring drought to Indonesia and Australia, La Niña tends to bring above-average rainfall to the same regions, sometimes heavy enough to cause flooding of its own. Where El Niño tends to suppress Atlantic hurricane activity through increased wind shear, La Niña tends to reduce that shear, generally producing more active, sometimes considerably more active, Atlantic hurricane seasons. Where El Niño tends to bring wetter conditions to the southern United States, La Niña tends to bring drought risk to that same region, a pattern that has repeatedly compounded water shortages across the American Southwest. Niño also has a notable tendency to persist longer than a typical El Niño event, sometimes lasting across 2 or even 3 consecutive winters rather than resolving after a single season. Between 2020 and 2023, the Pacific experienced exactly this kind of extended episode, an unusually long stretch of La Niña conditions spanning 3 consecutive winters, a sequence rare enough in the historical record that meteorologists took to calling it a triple dip, La Niña. That extended cool phase gave way to the strong El Niño of 2023 and 2024, illustrating just how directly these 2 phases of the same cycle can follow one another. Cool giving way to warm within the span of a single year once the underlying feedback loop tips in the other direction between these 2 extremes sits. A third condition, one that in fact describes most years, ENSO neutral, a state in which the tropical Pacific sits close enough to its long-term average that neither an El Niño nor a La Niña is declared. Roughly speaking, across any given multi-decade stretch, the Pacific spends something close to half its time in this neutral condition, with the remaining time split unevenly between El Niña and La Niña episodes of varying strength and duration. There is one further layer of nuance that ENSO researchers have only fully appreciated in the past 2 or 3 decades, and it complicates the simple picture of El Niño as a single, uniform phenomenon that merely varies in strength from one occurrence to the next. Careful analysis of sea surface temperature patterns has revealed that not every El Niño warms the Pacific in quite the same place. Some events, generally called Eastern Pacific El Niños, produce their strongest warming close to the coast of South America, in the classic pattern described by Bjerknes and observed in 1997 and 2015. Others, generally called Central Pacific El Niños, and sometimes given the more descriptive but less formal label El Niño Modic, produce their strongest warming further out in the middle of the ocean basin, closer to the international dateline, with comparatively modest warming near South America itself. This distinction matters because the 2 flavors of El Niño appear to produce somewhat different teleconnection patterns, shifting rainfall and jet stream behavior in ways that do not always match the textbook expectations built primarily around the classic Eastern Pacific pattern. The scientific community continues to actively debate exactly how meaningful and how stable this distinction really is, whether it reflects to genuinely distinct physical regimes or simply their natural range of variation. within a single underlying phenomenon, and research on the question remains ongoing. It is a useful reminder that even a pattern studied as intensely as El Niño still contains open questions at a level of detail beyond the basic mechanism, and that the categories scientists use to describe complex natural systems are tools for understanding, refined over time as evidence accumulates, rather than fixed boundaries carved into the ocean itself. All of this, the feedback loop itself, the century and a half it took to understand, the instruments built to watch for it, and the surprising reach of its effects across the planet, forms the backdrop against which the specific event now developing in the Pacific has to be understood. It is worth returning, at this point, to where this account began, the warm water detected sliding east beneath the surface in the spring of 2026, and to what forecasters have actually said about where it appears to be heading by the middle of May of that year. Weekly sea surface temperatures in the Niño 3.4 region had climbed to 0.9 of a degree Celsius above the long-term average, in a stretch of ocean larger than the continental United States, at a point in the year when many forecasters had still been expecting something considerably milder. The signal was clear enough that, on the 12th of March, NOAA's Climate Prediction Center took the relatively uncommon step of issuing a formal El Niño watch, placing the probability of a fully developed event emerging by July at 82%, and the probability of that event persisting through the following winter at 96%. By April, the Southern Oscillation Index, the very same atmospheric pressure Cecil Gilbert Walker first identified almost a century earlier, had fallen to negative 11.2, a reading consistent with exactly the kind of weakening trade winds that mark the early stages of an El Niño event taking hold. Michel Leroux, a physical scientist at NOAA's Climate Prediction Center who has spoken publicly about the developing forecast, has been careful to frame the outlook as conditional rather than settled. In her description, the ocean side of the equation is already doing what it needs to do, but the atmosphere still has to respond in kind, keeping the trade winds weak enough, and keeping warm water from sloshing back westward, for the Bjerknes feedback loop to keep running rather than stalling out partway through. Whether that coupling holds through the summer determines, in fairly direct terms, whether the event now forming becomes something historically significant or fades into a more ordinary, forgettable warming. The 2026 to 2027 event carries one further distinction worth noting. On the 1st of February of that year, NOAA officially completed its transition from the older Oceanic Niño Index to the newer relative version, described earlier in this account, meaning that this event will be the first in history to be monitored, classified, and forecast from beginning to end using the updated methodology. How its eventual peak compares to the very strong events of 1997 and 2015 may, as a result, depends somewhat on which version of the index is used to make that comparison. A reminder that even something as seemingly objective as a temperature reading carries a layer of methodological choice underneath it as for how strong the developing event might actually become. The range of expert opinion at this stage is unusually wide, and unusually confident at both ends of that range simultaneously. According to the Climate Prediction Center's most recent discussion, there is roughly a 2 in 3 chance that the event peaks as a strong or very strong El Niño during the November through January window, against a 1 in 3 chance that it ends up weaker than that. Some of the most closely watched forecasting models in the world are currently pushing toward the upper end of that range, into territory with no precedent in the instrumental record. The American Climate Forecast System has, at points, projected a peak in the neighborhood of 3 degrees Celsius above average for October and November, a figure that would exceed every El Niño ever measured, and the main European medium-range forecasting model has shown broadly similar peak values across parts of the same region. If either model proves correct, the event arriving by the end of the year would stand as the strongest ever recorded by modern instruments. What keeps forecasters from committing fully to either outcome is a complication that runs deeper than ordinary forecast uncertainty. The world this El Niño is developing within is not the same world the three very strong events of the instrumental record developed within. The entire tropical Pacific has warmed over recent decades, and so have the tropical Atlantic and the tropical Indian Ocean, in each case independently of whatever the Pacific happens to be doing on its own. There is growing evidence that the teleconnection patterns described earlier in this account, the links between Pacific warming and drought in southern Africa, flooding in Peru, and a quieter Atlantic hurricane season, may not behave in future events exactly the way the historical record suggests they should. A study published in the journal Nature in January of 2026 examined the El Niño event of 2023 and 2024 and found that its typical downstream impacts had been partially offset by unusual warmth in ocean basins outside the Pacific occurring at the same time, producing outcomes that diverged from what the standard historical playbook would have predicted. This points to something genuinely unsettled at the frontier of ENSO science right now. The teleconnection patterns that regional climate forecasting has relied on for the past half-century were largely calibrated against a period when Pacific warming stood out clearly, against a comparatively neutral background in the other ocean basins. When the Atlantic and the Indian Ocean are both running unusually warm at the same time as the Pacific, the atmospheric bridge that carries the ENSO signal outward toward the middle and higher latitudes is operating against a changed background state, and exactly where that signal ends up landing becomes harder to predict using patterns drawn from the past alone. The historical record remains the best available guide forecasters have. It has simply become a somewhat less reliable one than it used to be, and current research is actively working to understand why and what, if anything, can restore some of that lost predictability. James Hansen, the climate scientist who first testified before the United States Congress about the dangers of global warming back in 1980, has suggested publicly that even a moderately strong El Niño arriving over the following 12 to 18 months could push the global average temperature to roughly 1.7 degrees Celsius above pre-industrial levels, at least temporarily. He has also expressed doubt that the planet will meaningfully cool back below 1.5 degrees once this particular El Niño eventually fades. A view connected to his broader assessment of how quickly background warming has been accelerating independent of any single ENSO cycle. It is worth being clear that this is one scientist's read of an actively debated question, not a settled conclusion the wider climate science community has universally endorsed, and other researchers studying the same data have offered more cautious assessments of how much of any single year's global temperature can be attributed to El Niño alone versus the steady underlying warming trend. The alternative to a historic, record-breaking event is considerably less dramatic, and arguably just as plausible given current uncertainty. If the atmospheric half of the feedback loop fails to fully engage, the event could peak somewhere in the moderate range instead, producing a year that more closely resembles 2009 than 2016. A real, but comparatively unremarkable El Niño that registers in the data without reshaping global weather patterns the way its more intense predecessors did. Forecasters expect to know a great deal more within a few months of this telling. The ocean side of an El Niño event tends to commit to its ultimate trajectory by late summer, and once that commitment happens, it rarely reverses. Course, one piece of the picture has already resolved, at least for this particular year. On the 22nd of May of 2026, NOAA released its official outlook for the coming Atlantic hurricane season, and for the first time in a decade, the agency forecast a below normal season, projecting somewhere between 8 and 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes, compared with an average season's 14 named storms, 7 hurricanes, and 3 major hurricanes. The last time NOAA issued a below normal forecast was in 2015, itself a strong El Niño year, consistent with the wind shear mechanism described earlier in this account. A quieter hurricane season is about the closest thing to an unambiguous benefit that El Niño offers, and even that comes with a caveat forecasters are careful to repeat. A below normal season lowers the overall odds of a destructive storm, but it does not eliminate them, and quiet seasons throughout history have still occasionally produced individual storms capable of serious damage. There is a detail touched on earlier in this account that deserves a fuller answer, now that the underlying feedback loop has been laid out in full. Why El Niño arrives when it does, on no fixed schedule, sometimes returning after only 2 years and sometimes not for 7. Part of the answer involves a separate atmospheric pattern called the Madden-Julian Oscillation, named for the 2 meteorologists who first described it in the early 1970s. This is a pulse of enhanced rainfall and thunderstorm activity that forms over the Indian Ocean and drifts slowly eastward around the tropics over a period of roughly 30 to 60 days, weakening and reforming in a semi-regular rhythm distinct from the much slower Bjerknes feedback loop that governs El Niño itself. As this pulse of thunderstorm activity moves across the far western Pacific, it can produce short bursts of westerly wind, blowing briefly in the opposite direction from the usual trade winds, strong enough to nudge the ocean's tilted surface and, under the right background conditions, set off exactly the kind of downwelling Kelvin wave that then grows into a full El Niño event through the feedback loop described earlier. This does not fully resolve the mystery of El Niño's irregular timing, since not every westerly wind burst leads to a full event, and some El Niños appear to develop without a single obvious burst preceding them. But it does explain part of why the ocean atmosphere system behaves less like a clock and more like something closer to weather itself, sensitive to smaller, faster-moving disturbances layered on top of the slower feedback loop, capable of tipping the system in some years and not others, depending on timing and background conditions that current science still cannot forecast very far in advance. Researchers studying this interaction describe El Niño as an example of what is sometimes called stochastic forcing acting on a deterministic feedback loop, meaning that while the underlying physics of the Bjerknes feedback is well understood and largely predictable once it begins, the precise trigger that starts it running in any given year carries a genuine element of essentially random weather scale noise, which is part of why no forecaster has ever been able to predict an El Niño's arrival more than roughly a year in advance with real confidence. There is one more consequence of the tilted, sloshing ocean worth, including here, because it affects people directly in a way that rarely makes it into broader accounts of El Niño. As warm water shifts eastward during an El Niño event, Sea level actually drops measurably across parts of the western Pacific, sometimes by several tens of centimeters. As the water that had been piled up against Indonesia and the surrounding islands flows east toward South America. For low-lying Pacific island nations, this temporary drop can expose shallow reefs and harbors that are normally submerged, disrupting fishing access and, in some documented cases, stranding boats that depend on a minimum water depth to move safely between islands. La Niña produces the opposite effect, pushing even more water than usual into the western Pacific and temporarily raising sea levels there beyond what the long-term, slower trend of global sea level rise would predict on its own, for island communities already contending with the steady, decades-long creep of rising seas driven by a warming planet. The shorter-term wobble introduced by each swing of the ENSO cycle adds a layer of unpredictability on top of an already serious long-term challenge, occasionally masking the underlying trend in any given year and occasionally making it appear briefly worse than the long-term average would suggest. This layering of a short-term ENSO wobble on top of a longer, steadier warming trend connects to a larger question that remains genuinely unresolved among the scientists who study this system most closely as the planet continues to warm overall. Does El Niño itself change, becoming more frequent, more intense, or different in character from the El Niño of the past? Unlike many other questions in climate science, where decades of research have converged on a fairly settled answer, this one has not, and it is worth explaining honestly why some research groups, including a body of work led over more than a decade by the climate scientist Wenju Tsai and various collaborators, have found evidence in climate model simulations that extreme El Niño events, the kind capable of reorganizing rainfall across the eastern Pacific the way the events of 1997 and 2015 did, become noticeably more frequent as greenhouse gas concentrations continue to rise. In some model experiments occurring roughly twice as often compared to a stable, pre-industrial climate. Separate analysis looking backward rather than forward, comparing observed ocean behavior during the first and second halves of the 20th century, has found signs consistent with this idea, including an apparent increase of roughly 10% in the amplitude of eastern Pacific temperature swings between the earlier and later halves of that century. The Intergovernmental Panel on Climate Change, in its most recent major assessment, described its confidence in this general area with notable care, stating that there is medium confidence that both the amplitude of ENSO and the frequency of its most intense events since 1950 are higher than during the centuries stretching back to 1850, and possibly higher than at any point extending back as far as the year 1400. At the same time, other research groups working with different sets of climate models, or emphasizing different aspects of the same simulations, have reached more cautious or even contrary conclusions, and a genuinely comprehensive review of the scientific literature on this question would have to describe it, honestly, as unsettled rather than resolved. Part of the difficulty is technical. Global climate models, however sophisticated, have historically struggled to reproduce the fine details of the tropical Pacific's average temperature pattern with complete accuracy, and because El Niño emerges from a delicate, non-linear feedback loop layered on top of that average pattern, even small errors in how a model represents the everyday background state of the Pacific can meaningfully distort how that same model simulates El Niño's future behavior. This is part of why, more than half a century after Bjerknes first described the feedback loop mathematically, and despite an observing system, a forecasting infrastructure, and a body of published research that would have been unimaginable to Gilbert Walker. The single largest source of year-to-year climate variability on the planet still resists confident, long-range prediction of how it will itself evolve. One further complication worth including here is that the two flavors of El Niño described earlier in this account, the Eastern Pacific pattern and the Central Pacific pattern, do not appear to be responding to a warming climate in quite the same way. A number of modeling studies published in the past several years suggest that Central Pacific events may become somewhat more frequent as the planet warms, while Eastern Pacific events, though perhaps not occurring any more often, may grow more extreme in amplitude when they do occur, driven by a stronger coupling between ocean temperature and wind stress in that part of the basin as the upper ocean becomes more sharply layered under sustained warming. If this pattern holds, it would suggest a future in which El Niño does not simply become uniformly stronger or more common, but shifts in character, favoring more frequent moderate events of one kind alongside rarer but more extreme events of the other kind. A considerably more complicated picture than a simple headline about El Niño getting worse would suggest. Study published in the journal Nature in 2025 added an unexpected long-term dimension to this question, one drawn from several thousand years of coral-based reconstructions combined with climate model simulations, rather than focusing on the intensity of individual El Niño events. The researchers behind that study examined how long ENSO episodes in Niño and La Niña alike tend to last once they begin, and found that multi-year events, ones persisting beyond a single year rather than resolving after a single winter, have been growing steadily more common over the past 7,000 years, with the current era showing more of them than any point in that long record. The proposed explanation traces back to the thermocline itself, the same invisible boundary described early in this account. Over thousands of years, the tropical Pacific's thermocline appears to have grown shallower and more sharply defined, a change that allows ocean and atmosphere to couple more efficiently and, in doing so, allows both El Niño and La Niña conditions to persist for longer once they take hold. If this long-term trend continues alongside the shorter-term changes driven by recent greenhouse warming, it points toward a future Pacific in which El Niño and La Niña conditions occupy a larger share of any given decade, each event potentially running longer than its historical counterpart, layered on top of whatever changes occur in each event's peak intensity. None of this amounts to a confident forecast of what El Niño will look like a century from now. It amounts, more honestly, to a genuinely active area of research, full of partial answers, competing lines of evidence, and technical limitations that current climate models have not yet overcome. And it is precisely the kind of open question that keeps a field of study interesting long after its foundational physics has been worked out. Before returning to where this account began, it is worth widening the view one last time, because the Pacific is not the only ocean basin capable of producing something like this pattern, and the specific numbers cited earlier for the economic toll of past events deserve a slightly closer look at where they actually come from. The tropical Atlantic hosts a quieter, smaller relative of the same phenomenon, generally called the Atlantic Niño. The underlying physics is recognizably similar. Trade winds blowing east to west along the equator, warm water piling up against the coast of Brazil, cooler water upwelling off the coast of West Africa, and an atmospheric loop overhead that behaves like a miniature cousin of the Pacific's Walker circulation. The Atlantic version tends to run on a shorter, more seasonal rhythm than its Pacific counterpart, typically developing and fading within a single year rather than persisting across multiple seasons. And its basin is simply too small, and its resulting temperature swings too modest to produce anything resembling the global reach of a strong Pacific El Niño. Even so, Atlantic Niño events have been linked to their own regional consequences, particularly rainfall changes across West Africa and northeastern Brazil, and researchers studying the two basins side by side have found evidence that a strong Pacific El Niño can, in some years, influence conditions in the Atlantic as well, adding yet another layer to the already tangled web of ocean basins quietly communicating with one another. A separate pattern in the Indian Ocean, called the Indian Ocean Dipole and mentioned briefly earlier in connection with the Indian monsoon, follows a broadly similar logic again, with warm water sloshing between the eastern and western halves of that basin depending on the instant strength of the winds blowing across it, occasionally reinforcing the Pacific's influence on regional rainfall and occasionally working against it. Taken together, these three basins, Pacific, Atlantic, and Indian, are increasingly studied not as separate, isolated systems, but as three coupled ocean-atmosphere pendulums swinging within the same overall tropical climate, each one capable of nudging the others, the Pacific event most directly responsible for turning El Niño from a regional curiosity into a subject of serious international scientific and economic attention was not one of the three very strong events described earlier, but an earlier, more moderate one, arriving in 1972 and 1973. At the time, Peru's Anchoveta fishery was already under considerable strain from decades of intensive commercial fishing, and the arrival of warm water that year, suppressing the cold upwelling the fishery depended on, pushed the anchovy population into a collapse from which it would take years to recover. The event demonstrated, in stark economic terms, that policymakers could not easily ignore just how directly a change in ocean temperature thousands of kilometers offshore could devastate a national economy within a single season. And it helped motivate the surge of research funding and international cooperation that, over the following 2 decades, produced the Toga program, the Dow buoy array, and the Kane-Zebiak forecasting model described earlier in this account. In a very real sense, the vast observing and forecasting infrastructure now watching the Pacific in real time exists because of the economic shock delivered by that one 1972 event, layered on top of the scientific embarrassment of failing to see the far larger 1982 event coming a decade later. As for the trillion-dollar figures cited earlier for the economic toll of the 1982, 1997, and 2015 events, it is worth understanding, at least in general terms, how researchers arrive at numbers of that size, since the methodology itself is a genuinely clever piece of applied economics, because El Niño's timing and intensity are driven by ocean physics entirely unrelated to any individual country's economic policies, elections, or business cycles. Economists studying its effects can treat the event almost like a natural experiment, comparing how a given country's economic growth actually unfolded in the years following a strong El Niño against a modeled estimate of how that same country's economy most likely would have grown in the absence of the event, based on patterns drawn from other countries and other time periods with similar starting conditions. The gap between the real, observed outcome and this modeled counterfactual becomes the estimated cost of the event itself, applied consistently across dozens of countries and multiple decades. This approach is what allows researchers to arrive at global loss estimates in the trillions of dollars. And it is also why the same event can produce noticeably different total figures depending on which countries, time horizons, and modeling assumptions a particular research team chooses to include, which is precisely why the studies cited earlier in this account, examining the same historical events, arrived at broadly similar but not identical final numbers. Which brings this account back, gently, to where it started, the warm water detected sliding east beneath the surface of the Pacific in the spring of 2026, and the question of what kind of event it is actually going to become at this point. Everything on the ocean side of the equation appears to be in place. The Kelvin wave has been moving east for months. Subsurface heat content across the equatorial Pacific has been climbing steadily since the previous December. The Niño 3.4 region sits close to the formal threshold, with individual weekly readings already comfortably past it. The Southern Oscillation Index has fallen into territory consistent with weakening trade winds. In the language used earlier in this account, almost everything that needs to happen on the ocean's side of the feedback loop for a strong event to develop has either already happened or is actively happening as this is being written. What has not yet happened, and what will determine whether this becomes an ordinary strong El Niño or something historians of the subject end up discussing alongside 1982, 1997, and 2015, is whether the atmosphere holds up its side of the bargain through the summer months, keeping the trade winds weak enough for the feedback loop to keep running rather than stalling out partway through. Forecasters expect a considerably clearer picture within a few months of this telling. The ocean generally commits to its trajectory by late summer, and once that commitment happens, the system rarely reverses course before reaching its peak sometime between November and January. Whichever way it resolves, researchers will be watching the entire event unfold through the same layered, observing system described earlier in this account. Buoys anchored across the equatorial Pacific reporting subsurface temperatures in near real time. Profiling floats drifting through the wider ocean, recording heat content at every depth. And satellites overhead tracking the tilt of the sea surface to within a few centimeters. An observing capability that did not exist at all during the surprise event of 1982, and that has been steadily refined ever since. What may not be answerable for some time, and possibly not until long after this particular event has faded from the news entirely, is a quieter and in some ways more interesting question. Whether the categories built up over the past 3/4 of a century, weak, moderate, strong, very strong, and the informal super El Niño that headlines reach for beyond that, still mean quite what they used to mean. The instrumental record underlying those categories only extends back to 1950. The three very strong events available for comparison all developed in a cooler ocean, under a different baseline, feeding into teleconnection patterns that formed under different background conditions than the ones now in place. The methodology used to measure and classify them for decades was itself only just retired, replaced by a relative index designed specifically to account for a planet that keeps warming underneath the very categories used to describe it. Proxy records built from coral skeletons and lake sediment layers extend the story of El Niño back thousands of years and reveal genuine, sometimes dramatic natural variability, including hints that past events may have rivaled or even exceeded the intensity of anything measured by modern instruments. But none of those proxies, however far back they reach, can capture what happens when an event of that scale arrives inside a background climate as warm as the one the planet carries today. Because that particular combination, a very strong El Niño layered on top of a substantially warmed planet, has simply never occurred within the multi-thousand-year window those records can see into, in the most literal sense available to science. This is uncharted water, not because El Niño itself is new, and not because the physics described throughout this account is somehow different this time, but because the ocean this particular event is moving through has never hosted one quite like it before, and because the instruments now watching it are, for the first time, measuring it against a reference frame built specifically to account for that fact. It is worth sitting for a moment with why a subject like this remains genuinely interesting to scientists. Decades after Bjerknes first tied its pieces together, and long after its basic physics became a settled part of every introductory course in atmospheric science, part of the answer is scale. Very few natural phenomena on Earth involve an entire ocean basin and the full atmosphere above it acting, for months at a stretch, as a single coupled system. One whose influence reaches every inhabited continent through mechanisms as varied as shifting jet streams, disrupted fisheries, altered disease transmission, and changes in how much carbon the land surface can absorb in a given year. Very few subjects connect fluid dynamics, atmospheric physics, marine biology, epidemiology, economics, and paleoclimate as naturally as this one does, each discipline contributing its own piece to a picture that no single field could complete. A lone part of the answer is also that El Niño offers something rare in climate science, a recurring, large-scale natural experiment that nobody designed and nobody can switch off, arriving every few years with just enough variation from one occurrence to the next that researchers are still, after a century and a half of study, refining their understanding of exactly how it works, why it varies as much as it does, and how it might behave differently as the background climate it operates within continues to shift. Most of what humanity understands about how heat moves through the climate system, about how a disturbance in one ocean can reorganize, whether on the far side of the planet, and about how difficult it genuinely is to disentangle a natural cycle from a longer human-caused warming trend, has been learned by watching this one recurring pattern closely. Year after year, event after event, part of the answer, perhaps the simplest part, is that the story is not finished. Somewhere beneath the surface of the Pacific right now, the warm water is still moving east, exactly as it has during every El Niño that has ever been recorded, and exactly as it likely did for thousands of years before anyone was recording anything at all. Buoys anchored along the equator continue quietly logging its progress. Satellites continue passing overhead, measuring the tilt of the ocean surface to within a few centimeters. Forecasters continue refining their models with each new week of data, waiting to see whether the atmosphere will hold up its end of a feedback loop first described mathematically less than 60 years ago by a scientist working with instruments that would have seemed like something out of fiction to the Peruvian fisherman who first gave this pattern its name. None of that requires any sense of urgency to be worth paying attention to. The Pacific has been having this same conversation with its own atmosphere for longer than there have been humans around to name it, and it will keep having that conversation long after the particular event unfolding in 2026 has settled into the historical record, filed away alongside 1982, 1997, and 2015, or perhaps filed away in a category of its own. Whichever way this one resolves, the buoys will still be out there afterward, bobbing quietly in the swell, still measuring, still listening to an ocean that has never stopped moving, long before anyone thought to ask what it meant.